All right, one of my favorite units in AP Environmental Science, Earth systems. And so the theory of plate tectonics describes the movement of the actual lithosphere itself. We have plate tectonics, and then we have the tectonic cycle, which is the sum of all the processes that build up and break down the lithosphere. And so the theory of plate tectonics is a unifying theory. Brings scientists together from different fields of science who can agree at least essentially on this one concept. And we now know that the lithosphere consists of a number of different plates. Oceanic plates, they lie primarily beneath the actual oceans, whereas continental plates lie beneath the land masses. And the crust of these oceanic plates is this real dense and rich iron material, while the crust of all the continental plates is generally consists of mostly of what we call silicon dioxide. That's a fancy chemical name for the word sand, which is much less dense than actual iron. So the continental plates, they're lighter than the actual oceanic plates, and so they rise on top of that part. They rise on top of them. Ocean and continental plates float basically on top of the denser material that's underneath them. So their slow movements are driven by these convection currents underneath Earth's mantle. And the heat from the Earth's core generates these convection currents, which are similar to those in the atmosphere. Kind of reminds me almost of a lava lamp where, the heat from the actual center causes the wax in the lava lamp to move up, and then once the wax moves to the top, it finally gets cool enough, which when it gets cooler, it gets a little denser and it falls to the bottom. It's kind of like the same current generation or generating current situation there. And so this mantle convection drives continuous change. And the creation and renewal of Earth's materials, in some locations anyway, of the actual lithosphere, and the destruction and the removal of Earth's material happen at these very specific locations. Earth is covered by these tectonic plates, and most of which are in constant motion, even though we can't feel it and we don't realize it. And on this diagram here, the arrows indicate the direction of the plate movement. So new lithosphere is added at these spreading zones, and older lithosphere is recycled to the mantle in these subduction zones. So as these oceanic plates, as they move apart, rising magma forms new oceanic crust on the actual seafloor at the boundaries between those particular plates. So this process called seafloor spreading is shown here in this figure. And that's where oceanic plates meet continental plates. And so these old oceanic crust is pulled downward beneath the actual continental lithosphere and removed from the ocean bottom, and it pushed towards the center of actually the center of Earth. So if you ever wanted to journey to the center of Earth, then that's what you would have to do. You would have to hop on one of these plates that's technically being recycled in ocean spreading. So essentially in this process, the heavier oceanic plate slides underneath the lighter continental plate. This is best seen in the figure that was just previous on the screen. And we call this process subduction. So as a result from plate movement, we get subduction, which is the process of one crustal plate passing under another. And then, of course, we get volcanoes. And that's a vent in the surface of Earth that emits ash, gases, and, of course, that molten lava that turns into new crust material. Because the plates move, continents of those plates slowly drift over the actual surface of Earth. And as the continents have drifted, their climates have changed and their geographic barriers, that have formed, have had new formation, and some of them have been removed. And so as a result, species have evolved and they've adapted, whether it be slowly or rapidly, and some of them have even gone extinct. And in some places, as these plates have moved, a continent that straddled two plates or has broken apart has created two separate smaller continents or even islands. And these islands go to places with a really different climate region. So you may recall from an earlier discussion or lesson, allopatric speciation. And that's when species that become separated, they take this different evolutionary path. And so over time they evolve into two essentially separate species. And the fossil record tells us how these species have adapted to change that took place over a long period of geological time. Climate scientists, interesting enough, and ecologists can use this information to basically anticipate how species will adapt to relatively rapid climate changes that we know are happening on Earth today. And although the rate of plate tectonics and its movement is far too slow for us to really notice, geologic activity provides this real vivid evidence that the plates are in motion. And as a plate moves over a geological hotspot, heat from that rising mantle plume melts the crust and it forms a volcano. And if you remember, a volcano is a vent in Earth's surface that emits ash, gas, or molten lava. And volcanoes are a natural source of atmospheric carbon dioxide. They also put particulates and even metals into the atmosphere. And over time, as the plate moves, it passes over this hot spot, it can leave behind a trail of extinct volcanic islands, and each with its own chemical composition as the one before it. So the Hawaiian Islands are an example of this. Our Hawaiian Islands were formed by a volcanic eruption in the Pacific Plate, and that plate was traveled over a geological hotspot. And so this chain of inactive volcanoes currently to the northwest of Hawaii shows that those locations used to be over hotspots. And so the numbers here that you're looking at that are on the screen, they indicate where each area was located directly over a hotspot. And these are numerical numbers, and that's in millions of years. So this one is 0.75 million years. Alright, so you might remember that there are several different types of plates. And so there's a divergent plate boundary, and that's an area beneath the ocean where the tectonic plates move away from each other. There's seafloor spreading, which we've talked about, and that's the formation of new ocean crust as a result of magma pushing upward and outward from the Earth's mantle. And then there's a convergent plate boundary, and that's an area where plates move towards one another and collide. And when plates move sideways, slipping past each other, that's a result of transform fault boundary. So here in this figure we can see the three major different types of plates, or plate boundaries, I'm sorry. A fault is a fracture in the rock across where there is movement. So when this occurs, it is said that there is a high level of seismic activity, and that's the frequency and intensity of the actual earthquake experienced over a particular time. And a fault zone is a large expanse of rock where a fault has occurred. Fault zones, we also call them areas of high seismic activity, essentially, form in the brittle upper part of the lithosphere, where two plates meet or slide past one another. And in these large expanses of rock where the movement has occurred, the rock near the plate margins becomes fractured and kind of deformed. And so from this immense pressure exerted by the plate movement, we see these faults. We'll discuss faults and earthquakes in more detail later. But if two continental plates meet, both plate margins may actually be lifted, forming what we call a mid-continental mountain range. And that's how the Himalayas, in mountains that are in Asia, have formed, shown in this diagram here. So when both plates are composed of material of equal density, one does not get subducted under the other. Instead, they're basically forced into one another, and this force of the plate movement pushes material upwards in the process that we now know as formation of mountains. And so most plates on the continents move at about the same rate as your fingernails grow. Do you know how fast that is? That's about 36 millimeters, or about 1.4 inches per year. So while this movement is far too slow for us to even notice on a daily basis, the two plates underlying the ocean in the Atlantic have spread apart and come together twice over the past 500 million years. And this is causing Europe and Africa to collide with North America and even South America, and then just separate them again. So if you do the math, plate movement shows us that we can basically calculate the time it takes for these plates to move. So although the plates are always in motion, their movement, while it's really slow, is not necessarily a smooth ride. So imagine rubbing two rough and jagged rocks past one another. These rocks would resist the movement and get essentially stuck together. So the rock along the fault is also very jagged and thus it resists movement. But the mounting pressure eventually overcomes that resistance, and the plates give away and they slip very quickly. And when this happens, we call it an earthquake, which is a sudden movement of Earth's crust caused by the release of potential energy along the fault, causing a vibration or movement at Earth's surface. Earthquakes occur when the rock of the lithosphere basically ruptures unexpectedly, and that is along a fault. The plates can move up to several meters in just a few seconds. Earthquakes are common in these fault zone areas that we talked about, which are, again, areas of high seismic activity. You may have heard recently about the San Andreas Fault, which is in California, and that's a transform fault. The epicenter of an earthquake is the exact point on which the Earth's surface that is directly above the location where this rock rupture has occurred. And earthquakes are a direct result of this movement of plates and their contact with one another. The magnitude of the earthquake that has happened is reported on what we call a Richter scale, and that's a measure of the largest ground movement that has occurred during any earthquake period. The Richter scale, if you remember, it's kind of like, reminds me of the pH scale a little bit. It's a logarithmic scale, and a value increases by a factor of 10. So essentially, it's a log base 10, just like the pH scale. So for each unit increase, the magnitude has increased by a magnitude of 10 times. And that means it has caused 10 times as much damage as the next level.